Hello everyone, my name is Malika Arslan Nisar and I am a TA for this course Numerical Linear Algebra. So today we are in the final session of this course, final total session, and it will be just a 1 hour session, and I will touch on some of the important topics you have gone through the course, and we will solve certain numerical problems based on the same. So let's get started. So the first question is based on the Gram-Schmidt orthogonalization process. So the question is, using a Gram-Schmidt orthogonalization for the vectors u1 is equal to 2, 0, minus 1, 1, u2 is equal to 1, 2, 0, 3, and u3 is equal to 3, 0, minus 1 and 2. Okay. So find so we have to find an orthonormal basis for the given vectors using the given vectors by Gram-Schmidt orthogonalization process. So we know the steps for the same. The first step is that we randomly choose any of the vectors, either u1, u2, or u3, and we normalize it first. We make a unit vector. So v1 is nothing but u1 upon magnitude of u1, okay, which is equal to, as you do it, so u1 is 2, 0, minus 1, 1 transpose, and the magnitude is obviously 2 plus 1 plus 1, okay, yeah, which is equal to 2, 0, 0, 1. Oh, sorry, it's 4 here. It's equal to root 6. So v1 will be 1 over root 6 of 2, 0, minus 1, 1 transpose. So v1 we have 2 by root 6, 0, minus 1 by root 6, 1 transpose. Okay. So let me try to simplify. It will be root 6 by 3, 0, minus of root 6 by 6, and root 6 by 6. Okay, so this is our first v1 vector. Now moving ahead, we have to find a vector v2. Okay, so which will be u2 minus projection of u2 along v1. So that will be u2 dot v1 into v1. And if you simplify it, so okay, our u2 vector here we have been given as 1 2 0 3. So it will be 1 2 0 3. Okay, minus u2 dot v1 is what? u2 dot v1. So v1 is here and u2 is here. So and this will be root 6 by 3 plus 0 plus 0 plus root 6 by 2. Okay, into v1 vector. v1 is root 6 by 3, 0 minus root 6 by 6 and root 6 by 6. So this is basically 1 2 0 3 minus 5 root 6 by 6, okay, into root 6 by 3, 0 minus root 6 by 6 and root 6 by 6. Now when we simplify it, it will come out to be as minus 2 by 3, 2, 5 by 6 and 13 by 6. So this is basically our v2 vector. Now we need to normalize it also. So we have to make a unit vector out of it. So that is v2, okay, upon magnitude of v2. Okay, v2 vector upon magnitude of v2 vector. So you have to divide this v2 vector by its magnitude, and when you simplify it, let me write it this way. It comes out to be minus 2 into under root of 354 upon 177. Then 2 into under root of 354 upon 59. And 5 into under root of 354 upon 354. And the last one is 13 into root 354 upon 354. Okay. So this is our second vector, second orthonormal vector. Now moving to the third and the last step, okay, for this u3 vector, we will find a v3, okay, which will be equal to u3 minus projection of u3 along v1, okay, and minus projection of u3 along v2. So it will be simply equal to u3 vector we have already been given here. Then we have to find u3 dot v1 as we did in the previous step, and similarly we have to find u3 dot v2 into v2 for the u3 vector. We have to dot product with v2 as we did in previous step. So when you do this and simplify it, it will come out to be 6 over 59, then minus 18 over 59, then 22 over 59 and 10 over 59. So this will be our v3 vector. Again, v3 is not a unit vector here, so we need to divide it by its magnitude, okay, and when we do so, let me write it like this. It will be equal to 3 root 59 upon 180 minus 9 root 59 upon 118, 11 root 59 upon 118, and 5 root 59 upon 118. So you can basically call it v3 prime, okay, this as v2 prime, and v1 equal to v1 prime, or v1 prime equal to v1. So basically this v1 prime, v2 prime and v3 prime are the orthonormal bases for the vectors u1, u2 and u3 which had been given in the question. Okay. Now second question will be based on finding the RREF, rank, nullity, range space and null space of a matrix, which is one of the basic and most important topics of linear algebra. So find the RREF of the matrix A equal to, so matrix A has been given, which is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5, 6. Okay, so this is the matrix A. We have to find its RREF and hence find the rank, nullity, range space and null space. Okay, so you know that how to find the RREF. Basically all the leading entries of any row we have to make them as 1, okay, leading, and rest we try to make as 0. So in order to achieve the row reduced echelon form of any matrix. So in this case clearly I would want to make in this first column I would want to make 5 as 0. First we have to focus on this entry which is already n1, so we will leave it as it is. Then this 5 and 9 we need to change them to basically 0. Okay, so I will do 2 row transformations here. The first one is R2 is equal to R2 minus 5 times R1 and R3 is equal to R3 minus 9 times R1. Okay, and this will change our matrix to 1. The first row remains unchanged. In second row we have 0, minus 4, minus 8 and minus 12. And R3 is R3 minus 9 R1, that is 9 minus 9, that is again 0. This will be minus 8, minus 22 and minus 13. Now our first column is done. So we move to the next column. Okay, so basically now we have to focus on this entry. This is the leading entry for second row. So this we have to make as 1. Okay, so we will divide this entire row by minus 4 in order to make it 1, and after that we will focus on these 2 to make them 0. So our next row transformation will be R2 is equal to R2 minus R2 by 4. Wait a minute. R2 by 4. R2 minus. basically, okay, this is, wait a second, we can do simply r2 is equal to minus r2 by 4. Okay, it will change it into 1, 2, 3, 4. This is 0, this will be 1, this will be 2, this will be 3, and this one will be 0, minus 8, minus 22, and minus 30 to remain as it is. Okay, now we have to focus on these two elements 2 and 8 in order to make them 2 and minus 8. We have to try to make them 0. So I'll do again two row transformations here. First is r1 equal to r1 minus twice r2, right? And r3 will be r3 plus 8 times r2. Okay, so it will be 1, 0, minus 1 and minus 2. The second row remains unchanged, and the last row will be 0. Minus 8 plus 8 is 0, so it will be, and it will be minus 22 and minus 30. Okay, I hope it's clear till now. Now similarly, we focus on the third column and we try to make this as this minus 22. We try to make it as 1. So what we do here, wait a second, I think I made some error here. 0, 0, yeah, sorry, I have not changed them. So minus 22 plus 8 2s are 16, it will be minus 6, and minus 30 plus 8 3s are 24, it will also be minus 6. Okay, now yeah, so what we will do, our next row transformation will be again dividing r3 by minus 6, or simply minus r3 by 6. So it will become as 1, 0, minus 1, 2, 0, 1, 2, 3, and the last row will be 0, 0, 1 and 1. Okay, now again we have to try to make these two entries as 0. So what we do is we simply r1, we will add r1 with r3 in order to make that equal to 0, and these first two entries will remain unchanged because the last first two entries of row 3 are 0. So r1 is equal to r1 plus r3. So it will change the matrix as 1, 0, 0, minus 2 plus 1, or sorry, it's minus 2 here. So it will be minus 1, then 0, 1, 2, 3, and it will remain unchanged again. Okay, now this 2 entry we have to try to make it 0 as well. So we will simply do r2 is equal to r2 minus twice r3. Okay, and it will not change the first two entries. It will 1, 0, 0, minus 1. The first row remains as it is. The second row 0 minus 0, 0, 1 minus twice 0, it will be 1 only. Then 2 minus 2 will be 0, and 3 minus 2 will be equal to 1. And the last row is 0, 0, 1 and 1. So you can see the first three columns here are linearly independent, and yeah, we have reached our row reduced echelon form, which we simply call as RREF. Now here there are three independent columns here. So we say that the rank of this matrix is 3, right? Now what about nullity? We know that rank plus nullity is equal to the number of columns, which is 4. So nullity will be 4 minus 3 equal to 1. Now for the range space, as you can see here, uh, these three vectors are linearly independent and they form the basis. So basically these three vectors 1, 5, 9, 2, 6, 10 and 3, 7, 5, they form the span of the range space. So we can simply write range space is span of vectors, column vectors 1, 5, 9. The second one was 2, 6, 10. And the third vector is 3, 7 and 5. So these three form the span of the range. Okay. Range space. Now null space. We know that null space is Ax is equal to 0. Okay, so instead of A here, we write the row reduced echelon form, that is 1, 0, 0 minus 1, 0, 1, 0, 1, then 0, 0, 1, 1. Okay. And what was our x? X we can write as x1, x2, x3, and x4. So this is basically equal to 0. Now from here, first equation is x1 minus x4 is equal to 0. Then x2 plus x4 is equal to 0. And x3 plus x4 is equal to 0. So from here, this x4, we have only 3 equations and 4 unknowns. This x4 is extra, so we express everything in terms of x4. So we write basically x1 is equal to x4, okay, x2 is equal to minus x4, x3 also is equal to minus x4, and x4 is simply equal to x4. So we have represented the 3 variables in terms of the fourth one, that is x4. Now we can simply write x is equal to x4 into 1, minus 1, minus 1 and 1. Okay. So put x4 is equal to 1. It implies x is equal to 1, minus 1, minus 1 and 1. Okay. So we can simply write null space is the span of this vector. Okay. So basically this is the null space. I hope this is clear. You can note it down if you want to. Please give me a moment. Meanwhile, you can note this down. Okay, so if you have noted this down, we can move to the next question. So the next question is based on the finding the condition number of matrices. Okay, so using two norm, find the condition number of the matrix 2 0 0 4. So we know that the condition number of a matrix is really very important to comment on its sensitivity, etc. Okay, so of any system. So how do we find the condition number for this matrix? We simply know that K2 of A, okay, is equal to norm of A into norm of A inverse. Now, by definition, what is norm of A equal to 2 norm of A? Okay, we know that 2 norm of A is equal to the under root of the maximum of eigen values of A transpose A. Okay, so the maximum among the eigenvalues of A transpose A, when we take its root, that is equal to the 2 norm of A. So here we have this. We since it is a 2 cross 2 matrix, we know that A transpose A here is equal to what? It is a diagonal matrix, right? And A transpose A is simply equal to A square, which is equal to 4, 0, 0 and 16. And being a diagonal matrix, we know that the eigenvalues are nothing but simply the diagonal entries of this matrix, which is equal to 4 and 16. So lambda max here is equal to 16. Therefore, 2 norm of A is equal to what? Under root of 16, which is equal to 4. Now similarly, for A inverse, okay, finding the 2 norm of A inverse, okay, will be what? Maximum of eigenvalues of A inverse transpose into A inverse. Now for that we need to first find A inverse. Okay, since it's a 2 cross 2 matrix, it will be simply we have to reverse the diagonal entries and divide by its determinant. So it will be simply 1 by 2, 0, 0, 1 by 4. Or simply we can say that it's a diagonal matrix, so we have to take inverse of every diagonal element, and that will be A inverse. So it is basically 0 0.5, 0, 0 and 0.25. Right. Now what will be A inverse transpose into A inverse? It will again be for a diagonal matrix equal to A inverse square. So that is nothing but 0 0.5 square, which is 0 0.25, 0, 0, and 0 0.25 square will be 0 0.0625, right? Now here lambda max will be what? It's clear that it's 0 0.25. So norm of A inverse is what? Under root of lambda max, which is equal to 0 0.5. Therefore, K is equal to norm of A into norm of A inverse, okay, which is equal to 4 into 0.5, which is equal to 2. Okay. So I hope this is the K2 norm. Okay. Um, I hope this question is clear. It was a basic question just to brush up what you have already learned, because you have done many problems on this. Now the fourth question I'm taking here is based on the eigenvalues and eigenvectors of the matrix, because this is one of the most important topics in linear algebra. Basically, if you see every method, we have QR decomposition, we have SVD and householder matrices, Jacobi, matlab whatever we studied till now, basically it came down to finding the eigenvalues and eigenvector of the matrices. So the basic method to find the eigenvalues and eigenvectors of any matrix is, we simply know that we find the characteristic equation of the matrix. After finding the characteristic equation, we find its roots and we say that they are the eigenvalues of the matrix. And for every eigenvalue, we calculate its eigenvector. So here also we have to do the same thing. Find the eigenvalues and eigenvectors of the matrix. Okay. The matrix has been given as 1, 1, 0, 2, minus 6, 2, and 5, 4, 7. So this is basically our matrix, call it A, okay, and we have to find the eigenvalues and eigenvectors for it. So first of all, what we do, we find the characteristic equation, that is A minus lambda I, determinant of A minus lambda I is equal to 0. So you can quickly try to find this, okay, then we can go through the solution. So okay, this will be simply equal to 1 minus lambda, 1, 0, 2, minus 6 minus lambda, 2, 5, 4, 7 minus lambda is equal to 0. Okay. Simplifying, it is 1 minus lambda, minus 6 minus lambda, into 7 minus lambda, minus 8. Okay, then minus 1 into 2 times 7 minus lambda minus 10 is equal to 0. It will be 1 minus lambda into 7 6 are minus 42 plus lambda square minus 7 lambda plus 6 lambda minus 8, okay, minus 1 into 14 minus 2 lambda minus 10 equal to 0, which is equal to 1 minus lambda into, this is lambda square minus lambda and minus 50 minus, it is 14 minus 10 is 4, so it will be minus 4 plus 2 lambda is equal to 0. Okay. Now simplifying this further, okay, we have, it will be lambda square minus lambda minus 50 minus lambda cube plus lambda square plus 50 lambda minus 4 plus 2 lambda equal to 0. So it will be minus lambda cube plus 2 lambda square, yeah, plus 51 lambda, okay. And minus 4 minus 50 is equal to minus 54 is equal to 0. So we have a cubic equation here whose roots we can simply find on any scientific calculator, okay. So you can quickly find it, okay. In the matrix, in the calculator, you can simply find the roots up to the cubic equation easily. I have already done it. So lambda 1 is equal to minus 6.74, lambda 2 is equal to 7.70, and lambda 3 is equal to 1.03. Okay, so these are the values for our lambda. Now finding the eigenvectors corresponding to each eigenvalue. It will be simply A minus lambda I equal to x is equal to 0. So we have to find the x or the solution for this equation. So for lambda equal to minus 6.74, it will be simply 1 minus lambda, that is 1 plus 6.74, okay, and the remaining entries are as it is 1 and 0. The second one is 2 minus 6 minus lambda, that is minus 7 plus 7, let me write it like this, yeah. So this is the second entry and the third one is 2 as it is. For the final row also it is 5, 4 and 7 minus lambda. So 5, 4 and 7 minus lambda is 7 plus 6.74 into x1, x2 and x3 is equal to 0. So it will be what? 7.74, 1, 0, 2, and this will be I guess, yeah, 0.74, 2, then 5, 4 and 7, 13.7. Okay, and it is x1, x2 and x3 is equal to 0. So basically this is just like finding the null space, okay, as we did in previous question. So I will simply tell you what the value is coming out to be. Okay, it's basically equal to the you can say the v1 vector corresponding to lambda is equal to minus 6.74 is, okay, it is simply equal to 0.53 minus 4.091. Okay, you know how to do it. We have done it in previously also many times. Now similarly for lambda equal to 7.70, we have v2 is equal to, I have already done it, 0.022, 0.149 and 1. And for lambda equal to 1.038, we have v3 equal to minus 1.15 minus 0.04 and 1. So you can try it at your own places also to find these vectors and see if you're getting the same. Now moving to the next question. Okay, so next question is based on the QR factorization, QR decomposition. So this is also one of the important topics of linear algebra. So we have been given a matrix A and we have to find its eigenvalues using QR decomposition. Okay. So the question is using QR decomposition. You can say QR decomposition or QR factorization. Find eigenvalues of A is equal to 4, 2. Okay. So basically the idea here is that using QR decomposition, we make this A matrix as a diagonal matrix. Okay. So the non-diagonal elements will be, non-diagonal entries will become 0 as we keep on moving the QR decomposition, and the diagonal entries, they will become equal to the eigenvalues. Okay, so now here we have been given A and A is equal to QR. Okay, that is simply how the QR decomposition works. So since there are many ways to find this QR decomposition for A, but here since we have been given as a 2 cross 2 matrix, so we can simply write it as A minus B, B and A. Why so? Because we know that Q is an orthogonal matrix, and here the condition is A square plus B square is equal to 1, and R is something which is an upper triangular matrix, so we will keep it as CD, E and 0. Now our A is equal to 4, 2, 2 and 3, and we have to write it as this. Now multiplying these two matrices, it is AC, then the second will be AD minus BE, the third entry will be BC, and the last entry will be BD plus AE. Okay, so from here AC is equal to 4, BC is equal to 2, and A square plus B square is equal to 1, AD minus B is equal to 2, and BD plus A is equal to 3. So from equations 1 and 2, we know that A square plus B square into C square is equal to what? This BC is equal to 2 here. Okay. Yes. So it will be 4 square 16 plus 2 square 4, that is 20. So C is root 20, which is equal to 2 root 5. And substituting this value of C in above two equations, we find AC is equal to 4 implies A is equal to 2 upon root 5, and BC is equal to 2 implying B is equal to 1 upon root 5. Okay. Now putting these values in the equation, AD minus BE is equal to 2. Okay. We find out D is equal to, okay, from here 2D, 2D minus E will be equal to 2 root 5, and from the equation BD plus AE is equal to 3. When we simplify it, it becomes 2 plus D plus 2E is equal to 3 root 5. Now using these two equations, we get D is equal to 7 by root 5 and E is equal to 4 by root 5. Okay, so now we have basically found out the values of Q and E, Q and R matrices. Okay, now the Q is, let me call it as A is equal to Q1 R1. Okay, so our Q1 is 2 by root 5 minus 1 by root 5, 1 upon root 5 and 2 by root 5, and our R1 is simply 2 by root 5, not 2 by root 5, it's 2 root 5. Okay, 2 root 5, then 7 by root 5, then 0, then 4 by root 5. I have simply substituted the values of A, B, C, D into the matrices. Okay, now what we do, we find the matrix A1 which is equal to R1 Q1. Okay, so as we multiply R1 with Q1, I have previously done it, so you can do this multiplication on your own end. We get that first R1 into Q1 is 5.4, 0.8, 0.8 and 1.6. Now this is our A1 matrix. You can see that the non-diagonal entries are coming close to 0. That is the purpose of our QR decomposition. Now for this A1 matrix, we again find Q2 and R2 in the same way as we did earlier. I have done it. So Q2 is equal to minus 0.9892. You can do it on MATLAB to see. Okay, so this is coming out to be 0.9892. Okay, this is our Q2. And similarly, our R2 is coming out to be minus 5.4589 minus 1.0258 0 1.4655. Okay, now using this Q2 and R2, again we find A2. So A2 is nothing but R2 Q2, and when we multiply R2 with Q2, we get a matrix equal to 5.5503 minus 0.2148 minus 0.2148 and 1.4497. So you can clearly see that again that non-diagonal entries are tending towards 0, and that is how basically QR decomposition works. Now from this A2 matrix, what we do, we again do the QR decomposition for A2 matrix and we find Q3 and R3. So Q3 for A2 matrix is equal to minus 0.9993, 0.0387, 0.0387 and 0.9993. And similarly our R3 we do as in step previous. This is minus 5.5545, 0.2707, 0 and 1.4403. Now see here, this Q3 and R3 we have found out. Okay, again our A3 matrix will be what? R3 into Q3, and when we multiply these matrices it comes out to be 5.5608, 0.0557, 0.0557 and 1.4392. If we consider up to the first decimal place only, okay, if we consider significant digits up to the first decimal place only, we can see that the non-diagonal entries have almost become equal to 0. So here we stop. Okay, so the diagonal entries are our eigenvalues. So the eigenvalues for A matrix are as 5.5, okay, approximately, and 1.4. So you can check this by finding the characteristic equation and then finding the eigenvalue also. So basically keyword decomposition works. I think this much is sufficient for today. We have like some of the important topics we have covered, and apart from that you can keep on practicing more and more questions. There are so many topics in the linear algebra overall. So I think this much is sufficient for today, because we are also running out of time. It's already 1 hour, and so I don't want to take much of your time. So